Okay, so this is going to be Recitation 9A. It's probably going to be maybe 2 or 3 recitation number 9s. In this recitation, we're going to just cover and review Chapter 18. Obviously, Chapter 18 is aldehydes and ketones. First part of Chapter 18 is just the basic information, structure, and reactivity of aldehydes and ketones. Then next part is need to know the IUPAC naming for aldehydes and ketones. So both when they're the main chain functional group and also when they're a substituent. The next part of the aldehydes and ketones chapter is the reactions. So when it comes to reactions, first thing is knowing how the aldehydes and ketones are made. So this raises the general point of how we're going to study these functional groups. So more precisely, the reactions are going to be viewed in terms of functional group interconversions. So starting material functional group gets converted into product functional group. That's achieved by a certain set of reagents. That set of reagents delivers a particular transformation, for example, addition, elimination, substitution. And then the detail of that reaction class is then covered in the mechanism, right? So is it substitution? If so, well, is it nucleophilic or electrophilic substitution? If it's nucleophilic substitution, is it SN1 or is it SN2? Is it nucleophilic aromatic substitution? If it is it addition elimination or is it elimination addition, and so on. So if you're going to view reactions in terms of functional group interconversions, then the first thing you obviously need to do is be proficient in your functional groups. So what we mean by that is a functional group is a unique arrangement of atoms and bonds. It is characteristic. It is unique to one functional group name. So obviously you already know this. So alcohol is when you have sp3 hybridized carbon connected to an oxygen connected to a hydrogen. And that's different to an ether, where you have carbon connected to oxygen connected to carbon. So these unique permutations of atoms and bonds, I like to call them structural motifs. There is a unique characteristic structural motif that connects a functional group name to a structure. So functional groups in terms of names and in terms of structures, those things are interchangeable. So obviously for aldehydes and ketones, aldehyde you have to have a CO double bond, but you have to have at least one hydrogen connected to that carbon of the CO double bond. But for a ketone, you need 2 carbon-containing substituents connected to the carbon of a CO double bond. So we're obviously limited in the elements that we have. So it's the detail of exactly how these atoms are bonded together. Number of bonds, sequence of atoms in bonds. This requires attention to detail. So any functional group that is mentioned in a chapter is fair game. You should know it. Obviously, because all your exams from now on are going to be open book, I can tell you all the answers are in your notes. So as long as you have access to your notes, you should be able to recognize and identify all these different functional groups. You might say, well, if the tests are going to be open book, why do I need to learn? It's because you need the understanding of that information and then how to apply it. So the first thing is that you understand and can recognize all of the different functional groups that are mentioned in chapter 18. And there are a bunch. So like you need to know obviously alkene or alkyne. As you go through the summary at the end of the chapter, you'll see one way of representing reactions is to state the name of the functional group and then the functional group of the product, right? So the top entry in the first table in your aldehydes and ketones summary says alkene, right? So alkenes, things that have a carbon-carbon double bond, can be converted into aldehydes and ketones, right? That's so the oxidative cleavage process from our alkene chapter. So also known as ozonolysis using O3, which is ozone, and your dimethyl sulfide. So alkenes can be converted into aldehydes and ketones. That's what the first line in the table at the top of your summary page says. So that's chemistry stated in terms of words. But you should understand that there's a corresponding structure that correlates or corresponds to alkene. And there's corresponding structures that are aldehydes and ketones. So you need to not only express these in words, but also be able to understand them in terms of structural or atomic change. So for the aldehydes and ketones, you need to know all the different ways to make them. So you have to put these in the context of functional group interconversions. What functional groups can I convert into aldehydes or ketones? Your lecture notes contain detailed examples of that. The end of chapter summary obviously has them summarized. The first grouping is in the table. This is a description using words. So alkenes can be converted into aldehydes and ketones. Aromatic systems can be converted into aromatic aldehydes or ketones by either Friedel-Crafts acylation or the Gatman-Koch formulation. Terminal alkynes can be converted into aldehydes. So that would be your anti-Markovnikov addition of H and OH. Obviously that gives you an enol. Enol reverts to its more stable keto form. The term keto, K-E-T-O, refers to a CO double bond. So the keto form of the enol in that particular case is actually an aldehyde, right? So there's a difference between keto and ketone. Aldehyde and ketone are functional groups. Keto is describing one form of a tautomer. So alkynes, if you do the Markovnikov orientation, addition of H and OH will give you ketones. We then talked about the dithiane ring. That's where you deprotonate and alkylate. And if you do that once, followed by hydrolysis, you get an aldehyde. If you deprotonate, alkylate, deprotonate, and alkylate a second time, followed by hydrolysis, that's how you get your ketone. So that deprotonation occurs at the carbon between the two sulfurs. Those two sulfurs, being more electronegative than carbon, render the carbon between them partially positive, and therefore that has the effect of acidifying those hydrogens. And then lastly, in that first part of the summary table, you have nitrile reacting with a Grignard that would give you what we're eventually going to learn as an imine that then gets hydrolyzed to the ketone.